All right, guys. I want to discuss some of at least one of these examples towards the end of the 1.4 notes, and then we'll jump into 2.1. 2.1's stem and leaf plots. You guys ever talk about those before? So you should have done those, huh? Well, we're at the end of chapter 1, huh? Well, if we were going to take a test after chapter 1, I would have told you before we got halfway through the last section. So the way we're going to, huh? Yeah, but those are quizzes. Those aren't like tests. We always give you at least like 3-4 days ahead time. The way the first test will be done is be a unit test over the first and second chapter, and we get to the third chapter is probability, so that will probably be a individual test. So as we progress, I don't always do with my college classes. I don't always do just chapter by chapter tests. Okay, sometimes I'll cluster 2 chapters, or then go back to 1 chapter, and then maybe cluster 3 chapters or something like that. So that's the way the first one's going to take place. If we go to 1.4, and if you haven't done or printed off the notes for 2.1, there's not a whole lot that we're going to write. We're going to make like 2 charts, stem and leaf plots, and you'll be okay without having it printed off today. So this example says the Smell and Taste Treatment and Research Foundation conducted a study to investigate whether smell can affect learning. Okay, yeah. Have you guys ever, like you've heard like eat peppermint when you are like trying to learn something, and then when you are being assessed or taking a test to like eat the peppermint again, and that can trigger like memory recall and retention. You can do the same thing with chewing gum. When I was in school, this was like I was in like 5th and 6th grade, we used to have proficiency tests, which would have been like you guys' end of course exams and that kind of stuff, but we had them in middle school. We had them like every 2 years or something like that. Like they would always put some kids in a classroom where it was like dead silent with lights on. Other kids had choice to go to a room that's dead silent, lights off. Some had lights with music. Some had lights with no music. And because there were studies being done that showed for some people that there was increased performance in those certain environments. Does that make sense? So that's what they're kind of doing here with something like this, that they're trying to say, does the smell of these certain masks impact learning? Okay, so subjects completed mazes multiple times while wearing masks. So they put them through something that they could easily learn with or without. So that's not saying that they're going to give them like an algebra test or a calculus test where maybe they don't have the capability of learning that stuff regardless of the mask. Does that make sense? Okay, so they put them through a routine that allows them to demonstrate a learned concept. It says they completed the pencil and paper mazes 3 times wearing floral scented mask and 3 times with unscented mask. It says participants were assigned at random to wear the floral mask during the first 3 trials or during the last 3 trials. It says for each trial, researchers recorded the time it took to complete the maze and the subject's impression of the mask scent, positive, negative, or neutral. Okay, so it says describe the explanatory and response variables in the study. So what are we trying to measure? Like I said yesterday, I always like to go to the response first. What are we trying to measure? Or what are we trying to see a change in? Anyone? Why are we putting masks on? We're trying to... Yes, which is correlating back to whether we're learning, right? Okay. So we want to see a change or a response in level of learning. Okay. Level of learning, maybe you could say rate of like the maze completion. Does that make sense? Okay. Which then we would correlate to saying that there was learning being done, okay, a higher level of learning. What would be the explanatory variable? What is the thing that we're doing that is going to potentially change the level of learning or the rate in which the mazes are completed? Yeah, the mask that they were. Okay. So the scented mask would be the explanatory. Okay. Is that okay there? Does that make sense to everyone? Okay, get quiet. Okay. So what are the treatments? So what are the things that we're doing? And so the treatments are always going to be related to the explanatory variable, right? The thing that we can control, the thing that we change to see if there's a change in the response. And so what are the treatments that we're doing? Are there, says they completed the pencil and paper mazes 3 times wearing floral scented masks and 3 times with unscented masks. Do you see how that's the thing that we're controlling? Whether I put a floral mask on you or a no scented mask or unscented mask, that is the treatment. Is that okay with everybody? So that's the idea. If we go back to the examples we did yesterday, that's like giving somebody aspirin or not giving them aspirin. Okay. So scented or unscented masks would be the 2 treatments. Okay. It says identify any lurking variables that could interfere with the study. Anything that could interfere with the study that we might think. So when we say lurking variables, it's not going to be written up there. You got any ideas of something that could maybe interfere with whether this is good? Okay, so if obviously, so what you're saying is that this is not a blinded study, right? Okay, so the participants know obviously whether they have the scented mask or the unscented mask on. So just because I have that unscented mask on, that might be a lurking variable that says, we've essentially got the placebo effect going on here. Okay, like I know I can smell it, so maybe I could just have that thought that I'm going to do better, and then they do better. Okay. What about maybe, would maybe fatigue of the people that are taking these tests be a lurking variable that we maybe don't know about? Okay. Maybe learning disabilities that may be underlying that we don't really know about. But it does say we try to randomize who my subjects are and when they wear the masks, right? Okay, so they even talk about, if I wear my mask, if I wear the scented one first and then I wear the unscented one, okay, that could be a variable that says, well, the person, now they know the study, they're trying to determine if the scent is something that would increase their learning. So they know the first 3 times they did this, they had the scent, and now the next 3 times they take it, they don't have the scent, so they think, I should be doing it slower then. Okay, so that might be a lurking variable. Does that kind of make sense? Your level of like involvement or response might be due to knowing that you should, because that's what the test is wanting, be slower without the scent. So those are some, and there might be others. Okay, so usually with lurking variables, like I said, when it's not written up there, they're not going to be text that says this is what's going on behind the scenes. We have to infer that. We have to think about different situations that might happen. Okay. It says, is it possible to use blinding in this study? I kind of talked about that, right? That'd be impossible because you as a participant know whether because you're using your senses, you know that you're getting one of the treatments or not. Okay, so you can't be blinded. Does that kind of make sense? We talked about observational experimental yesterday, right? Observational, or you're just kind of sitting back and you're watching. You don't control anything. A lot of times it's post-experience, meaning that maybe I'm looking at like end-of-course exams and of maybe 3 years of end-of-course exams where students were under this teacher's responsibility, and then I view those those students 3 years later underneath a different teacher's responsibility, and I'm just observing scores. I didn't control what teacher they had, right? I just observe the scores, pull the scores off, compare the scores, that kind of stuff, and then I can maybe make an analysis about the quality of teacher A or teacher B. Okay. So those types of things, when you're doing that, you're not manipulating anything. That is observational. These two examples that we did would be experimental, okay, where we actually controlled the variables, okay, the explanatory variable. We changed the degree of that variable, okay, and how we implemented it. We talked a little bit about ethics. There's it's called the Institutional Review Board that universities use, researchers use to make sure that we are holding each other accountable for their work, so that I can't, let's say that I want to prove with my student data that I'm a fantastic teacher, okay? I would have some inherent bias there, right? I would want to prove that. I've got self-interest in that study, okay? So I might skew the data, okay? I might manipulate the data. Does that make sense? Okay. Volkswagen did this several years ago. They were with the EPA. The emissions were supposed to be at a certain level, and I think it had to do with like the EPA has these standards for your emissions, and I think Volkswagen was trying to get underneath these criteria so they could have like a financial kickback. Does that make sense? And obviously it was a marketing thing as well, because if a lot of people are going to go buy a car that says, hey, low emissions, I'm going to save the planet, I'm going to do good things, they could use it as marketing. But it turned out that Volkswagen was actually manipulating their data. They were programming their the computers inside the cars to give false data back to their researchers. Does that kind of make sense? So, because they had self-interest in there, they didn't want to be fined by the EPA. They wanted to make sure they could sell their cars, that kind of thing. So there are bodies of review that studies go through. Okay, if there weren't, something like that would have gone through and nobody would detect it. And then there still are things that go through, even though we've got these review boards and we've got peer editing and peer review and all that kind of stuff. Things still slip through and get published and get media attention, that kind of stuff. And then it won't be for a while until somebody recognizes it and starts looking at that research and says, I don't know, and they start investigating it. There is a website, it's called retractionwatch.com, that just goes through and lists the survey or the studies that have been found out to be fraudulent. Okay, where somebody had some self-interest and manipulated data. Maybe it could be completely unintentional, but they unintentionally created a lot of bias, and their results were really unfounded. So they'll be on that site, so people can realize that. Does that make sense? Okay, so and that's the thing that I want you guys to make sure that we understand. When we're reading things, when we're studying stuff, anybody watch the debate last night? They talk about fact checking all the time, right? That's like the buzzword all the time anymore with media and social media, all that kind of fact check. That's what this is all about. These international review boards are essentially fact checking each other's surveys, and people lie. Okay, there were so many lies last night on both sides. Okay. It's then if you're an uninformed person and you just watch that, you might have thought these guys are telling me the truth, and I'm going to listen to what they say, right? But what most people do is, okay, I hear what they say, now I'm going to go research that stuff and see, are they telling me the truth? Are they lying? What degree are they lying? That kind of stuff. Does that make sense? You need to view statistics the same way. When you get a study, read it, review it. Go find other studies that maybe measure the same thing, read them, review them, compare them, and just keep digging and digging and digging and see if things make sense. Does that make sense? And you can then make your own argument about the results that are being provided. Okay? Now, the nice thing that we've got these review boards is that most of the time you're going to get something and say, yeah, that because it made through the review board, made through peer review, that we can argue that, yeah, that probably makes sense. Okay, and that's probably legit information they're giving us. But especially with things like new medicines and stuff like that, and maybe even like diseases that are rare. Like one study of a disease of somebody, a rare disease that maybe only 100 people in the world have, okay, there's not going to be a whole lot of studies about it, right? So the first study I read, maybe it's the only study I read, might give me some data that might really not be true. Does that make sense? Okay, it might be biased, it might be unfounded, and the hope is, okay, is somebody else doing another study to see if anything from this first study is kind of debunked or anything like that. Okay, so we always got to think about that. We always got to think about the human aspect of statistics, and that humans usually have self-interest. Humans usually can persuade people one way or another, okay, and know that, okay. A lot of people that are statisticians are, they're honest people, but there are those people out there that are not honest, right? Just like any other situation. So you should always be on the lookout for that. Something to do with research is, okay, so if I'm reading a study, it's going to have all the authors of that study. Maybe you do like biography searches on those people, okay? We look at, just an example of kind of what's going on right now in the world with the vaccines, okay? Dr. Fauci pushing vaccines, right? Okay, Google Dr. Fauci, and you find out that his wife is attached to vaccine, like a board of review for vaccines, and she is going to then be eventually financially benefiting off of vaccines. If you look at Fauci and Bill Gates, they have a close connection to, I think they were roommates at one point in college, okay? So those types of things you don't know just looking at things until you start researching those people. Does that make sense? And then you can understand maybe their studies and what they're trying to get people to think about. Okay, we could talk about that ethical stuff all day long. Okay, but those are always things to do. So getting into chapter 2, I think you guys are going to appreciate chapter 2 after going through chapter 1. For the mere fact that we're actually going to be doing things with data now, okay? So the calculation aspect of mathematics is going to be around now from pretty much here on out, okay? You want to stay in 2-1 or chapter 1? You like that stuff? Good. Okay. There's still going to be vocabulary, but it's not going to be like this entire chapter is vocabulary like chapter 1 was. Chapter 2 is all about creating, today, stem and leaf plots, which you guys have done before. Box and whisker plots, you guys ever done those before? Okay. I think that's like section 2.5 or 2.4. Histograms. Ever make a histogram? Bar graph. Okay. Ogive. Okay, an ogive is just a cumulative frequency graph. What are some other ones? Time series graphs, which you've made. You probably didn't call them that, though. Line graphs. And we'll also take more time to talk about frequency distribution tables. Those they just kind of show up all the time throughout the course. So spending several days and several sections on those is beneficial. But today, like I said, stem and leaf plots. So this is pretty straightforward. Like you guys have seen this before. But every one of those types of graph or chart has a pro to it and they have cons to them. Okay. The nice thing about stem and leaf plots is that they're going to allow you to recognize the mode quickly. What's the mode? So it's the data piece that shows up the most. Okay. We're going to be able to see that visually when we create our stem and leaf plot. The median will be a number that will be easily determined using stem and leaf plots, because stem and leaf plots automatically the way we set them up, structure your data in order, and then if I start from the beginning and the end and work my way to the middle, I can find my median, right? Okay. So those are the two, I would call those measures of central tendency. Those are the two that the stem and leaf plot allow us to find the easiest. A con to the stem and leaf is if your data is like you have a very large sample, stem and leaf plots can be kind of hard to construct. If I have 1,000 pieces of data, stem and leaf plot's probably not a good way to represent the data. You know, here I think we've got, you know, around probably 25 to 30 pieces of data there. It's not a terrible amount to work with. If my data was all like let's say we were talking about the ages of everybody in the high school, okay? You're all teenagers, right? So we're all 13 to probably 19, right? Okay. So I would have all my stems would be 1s, right? And then after that, I would just have a bunch of 3s, 4s, 5s, 6s, 7s, 8s, and 9s, right? So my stem and leaf plot would be just one row, not very informative. Does that make sense? Okay. So if your data doesn't vary very much, stem and leaf can be an issue. Okay, but then we have other tools that we can use to display our information. The stem is the larger unit or place value, and the leaf is the unit place. So if I'm looking at 32, the tens place is going to be my stem, and the ones place or my units place is going to be my leaf. Is that okay with everybody? All right, so I've already organized this data for us in order, which is beneficial. You're going to see in then one of the next examples we do how much of a pain in the butt it is if it's not already ordered. I like to just, you know, go through, since it's already, we got 33, so I put my stem down of 3 and my leaf of 3. Okay, and I'll cross the ones off that I've completed. So we got 42, so I'll put my stem of 4. We got a 42, and then we got two 49s, right? You need, if they repeat, you need to make sure that they repeat, okay? Because when I'm done, I should be able to count how many leaves we have, and that will tell me then how many were in my sample. Does that make sense? Where if I just put 49 in once, I mess my sample up, I mess up the, really all the other mathematical computations that we're going to do. So if it repeats, it needs to show in our list that many times. So we got a 53, we got a 55, another 55. 61, 63, 67, 68, 68, 69, 69. We got a 72, 73, 74, 78. And then we've got an 80, 83, 88, 88, 88. We got a 90, 92, a 94, 94, 94, 94, and a 96. And then we got 100. So I get to one. So all of these were 2-digit numbers, right? Okay, 33, 42, 49. Now we get a 3-digit number, but the progression is the same. So I was going 7, 8, 9, 10, and now that 0 there would tell me 100. Does that kind of make sense? You can see then essentially the clustering and the length of your leaves over there on the right hand side. You can kind of see that your data, most of your data, falls between the 60s and 90s range, right? That kind of makes sense? Okay, maybe we could say most of our data is above 55 and below 100. Okay, can I look at that right away and say, okay, look at the leaves. What number repeats itself the most up there? '94, right? Is it easy to see that these 4s here repeat more than any other leaf up there? Okay, so that automatically tells me my mode is 94. Okay. We're going to spend a whole lot of time doing this, but so with finding the median, you guys remember the rule or the procedure for finding the median is to basically say, okay, I'm going to put my numbers in order, and then I'm going to cross that one off and cross that one off, the first and last one, right? Okay, so that would be crossing that leaf off and that leaf. And then I'm going to go 42, cross that one off, and that should get to cross off with 96. So then I go 49 and 94, 49 again, another 94, and I can keep doing that process back and forth until we get down to the middle number, right? Does that make sense to everybody? Okay. So just to save time, I'm not going to do that, but you guys can list them like this, and we go starting from the top, starting from the bottom, and work our way to where we meet, and we can find our median. Okay. What if we get to the point where we just cross two things off, and now we have two numbers left over in the middle? Do you remember what we do with those? Oh, what's that? You split them. Okay. So we're going to average them. We're going to add them together, divide by 2, and the median then is that middle point. The median doesn't have to be one of your data points. Does that make sense? Okay. When I talk about the mode is always one of my pieces of data, but my median does not have to be, and neither does my mean when we talk about that. Okay. Is that okay with everybody? Can we do that? All right. What if I had, so I don't know if you guys are when you talk about mode, what if we had like 94 shows up 4 times? What if 49 showed up 4 times? Which one would we say was the mode? Both. Okay. So you can have what we call bimodal pieces of data or sets of data where the mode is shared. Okay, or two values represent the mode. This one here would have been what we call unimodal. Okay, it's got one mode. Okay, and you can, I mean, if you think about it, you could have trimodal, you could have quadmodal. I don't know if they call it that, but you can have 1, 2, 3, 4. You can have 10 modes if they all those data points are the same quantity, same multiplicity. If you remember from college algebra, that phrase. Okay, so here's a unique set of data. You guys don't have to write this down. I just want you to see this because it is something that people struggle with sometimes. If I've got my stem and leaf, so there's my stem, there's my leaf. I'm going to do the 1, 2, or the 12, the 13, the 21. So if I go 12 and 13, I go 21 and 22, and we got 35 and 42, right? How do I write 6? Okay, so I need to have a 0, 6 there, right? And that right there frustrates some people. Okay, they don't know whether to put something there and then 6 over here, leave that blank, put 6 over here, put 6 over here as the stem. Does that kind of make sense? Okay, so just be on the lookout for that. Another issue is, let's say that I jump all the way to like 70. 70 is my next data piece. Okay, well, I don't want to go from 4 to, because and I'll show you why. I don't want to go from 4 straight to 7. Okay, I'm actually going to write down the 5, the 6, and the 7, and now I've got that data point, right? And the reason I do that is, what do we call things that are not like the rest of the data? Outliers. Okay, so that visually helps me identify whether 70 could potentially be an outlier. That's one of the benefits of creating a stem and leaf, is that it structures things so that you can see, okay, this piece of data is not closely tied to the other, so that's potentially an outlier. Okay. Now, when we decide whether something's an outlier, it's that idea we talked about in geometry, like, you know, I might be close to Jenna now, okay, still might be close to her, so I might, in terms of being a piece of data, I might be close to the rest of the pieces of data right now where I'm standing, but now when I move here, I'm an outlier. Does that make sense? Well, does that mean I'm an outlier right here, or now am I still close to my data? So what we will do is we'll actually have a formula, because we need precision. We'll have a formula that actually allows us to take 70, run it through a calculation and say, okay, well, is 70 then an outlier compared to the yellow data or not? Okay, but it allows you to at least get an idea visually of what numbers to try to see if they're outliers. Okay. Questions on that? We're okay? That's what the next term here identifies. The outliers are sometimes called extreme values. When we find an outlier, it's usually then a good practice to maybe start to analyze why that value showed up, okay, why that piece of data exists in our sample. It could maybe open your eyes to maybe a poorly written question in your sample or your survey that provided the data. Could maybe, think about when we did our ages a couple days ago. Okay, my age was probably an outlier, right? And we could then argue that choosing of that sample created some inherent bias in it. Okay, so outliers, to be able to explain them, we need more information, and we would like to investigate them when we do see them. Let's kind of skip that. If one thing we didn't do here, when I see this stem and leaf plot, I don't know whether 33, 3 is a stem, 3 is a leaf, if that means 33 or it might mean 3.3. Okay. Same thing with 42. Does that mean 4.2? Does it mean 4.02? What does it mean to me? So I need to write a key. These usually show up at the bottom of your plot, and you'll say like 4, and then your line 2. So that's my stem, that's my leaf. And you'll say that is equal to 42. Okay. So if I'm doing this list here, we'll just do a couple of them. If this is my stem, this is my leaf. I'm going to have 1, 1, 1, and a 5. I'm going to have 2, 3, 2, 5, 2, 7. We'll have 3, 2, 3, 3, 3, 5, and 3, 8. I'll stop there. But if I look at that stem and leaf plot looks much like this one, right? This one was talking about integers greater than 30. This one here is talking about numbers between essentially 1 and 12.3, right? So I need to write a key here that says 1. I don't like to use the first value because especially in this case, it's 1 and 1. So I don't like to do that. I just don't like that picture. Doesn't really matter what data point you choose. Also, say 1, 5. I mean, that is to be 1.5. Is that all right, everybody? Doesn't even have to be a number. When you write your key, doesn't even have to be a data point that you have. Okay. Questions on that? All right. Something you've probably not done, but it's not hard, is what we call a side-by-side stem and leaf plot. Sometimes called a double stem and leaf plot. But it allows you to compare two sets of data in which you've collected the same characteristics or same information about two different groups. Okay. Or two pieces of data about the same group. So the example we're going to do, it's the same group, it's the presidents, and we're going to collect the data of when they were inaugurated, how old they were, and then how old they were when they died. Okay, so that's the same group of people, two different statistics about them, right? But we could also do maybe, if we were talking about maybe comparing both stats classes. Okay, maybe I could take the average grades for each student in first period, put them in a stem and leaf, and then take your guys' averages, put them in a stem and leaf, and I can compare first period to seventh period. Does that make sense? Okay, but we're going to put them side by side. So there's a little bit of different structure here. So first period, we found out that the way I had this inserted in here was kind of nasty, kind of hard to see. So bear with me. I apologize. Huh? You're not a big Taft fan? All right, so with a side by side, what you're going to do is you're going to put your stem in the middle, and you're going to have leaves on the right hand side and leaves on the left hand side. Now, each side, you're going to have to decide what data is going to follow here. So I can't have, like in this is when they were inaugurated. Okay, you cannot put like 57. If I have 5 here, I can't put like 57 here, and then come down here and say, oh, there's another 57, so that goes over there. Does that make sense? So I have to decide. So I'm going to put the age of inauguration over here, and I'll put the age of death over here. So we need to go through, and this is kind of what stinks about this example, and I'll fix this for upcoming years. But like this data is organized off of names, okay? Which, let me show you something real quick. If you ever run into, this is a benefit of using Excel. Let's see here. So let's say that I have like Washington. Let's just put, I don't know if these are accurate, but, and then let's go Lincoln, and then let's go Taft, since he's your favorite. You like Teddy? Yeah. All right, so let's say we have something like that. And obviously, we have a lot longer of a list, right? But if I wanted to sort this data based off of different criteria, what I can do is I can actually highlight this and come up to, I gotta find out where it's at. It should be here. It should be sort. They changed 365 on me, but formulas. There it is. Okay, so it's under data. But if I click on sort, okay, it's going to give me options on how I want to sort. So I want to sort by column A and sort on order. Let's go order A to Z and hit OK. And you see how it moved everything alphabetical for me? Okay. I can click on sort, and let's say I want to go column B, cell values. I want to go smallest to largest. See how it put everything smallest to largest for me? Okay. So it attaches those two, and those two, and then I can sort and move things around, and then we're going to move together. Okay. So that's a nice thing, which would help me then here constructing this stem and leaf if we would have done that. But if I go through here, I think the youngest age, we got some 40s, so 47. Got a 43. Hey, where did I miss it? Garfield. Man, I'm terrible at this. Right here. See any more? All right, so we got a 43. We've got a 42, so I should put that. So the way we read it, and this is important, you read it from the inside out. So the 2 needs to come first, then the 3, then I've got, what, a 46 in here. I've got 2 47s, a 48, and I think 2 49s. Does that kind of make sense? It's not chronological left to right. You're going from the inside out, okay? And if I go to the death side, come down here, this is the grouping for deaths. I think Garfield died early, right? Garfield died 49, and Kennedy was 46. So 46 and 49, okay? And then I would go to the 50s and do the same thing, right? What's going to happen here, I'll just kind of give you a visual. what's going to happen, obviously there were more people inaugurated when they're in their 40s, 50s, and 60s, right? So the visual is going to be, like, your numbers are going to be kind of like organized that way. Does that make sense? The older they get, the less inaugurated, the less quantity are inaugurated at that older age. But your death is going to be structured kind of like that, right? Not a lot of them died when they're 40. Not a lot of them died when they're 50. It's mostly when they're in their 70s and 80s, okay? So that allows you then to make the comparison of where your data clusters for these two different characteristics. Does that make sense, everybody? All right. Tomorrow we'll start talking about bar graphs, some line graphs. There is an assignment in Math Excel over 2.1. It's going to be open until Friday night. Okay, so why don't we give that a shot? It's not hard. There's a couple distribution table questions in it because I think those are things that we should continually talk about and see in practice. But most of it then is simile stuff.